So today we'll go into the final topic for the homework assignment, which is 1.4. We've covered factoring, and that's actually a big topic in 1.4. If you struggle in factoring, I will upload a factoring practice sheet that you can practice on. And if you need help, you can always ask questions. So 1.4 is all about rational expressions. Now, though it's rational, it talks about rational expressions, there are some concepts in there that are not rational expressions. So we need to discuss what is a rational expression. A rational expression is a polynomial a over is a polynomial a divided by polynomial b. I on e, it's going to be a over b. So example you might see is polynomials have terms and everything, and they also have variables. So let's take 3x squared plus 2 over x plus 1. This is an example of rational expression. Now, some fractions or some expressions written as a fraction are not rational expression. In particular, if you have a square root, let's say square root of x over x plus 1, this is not a rational expression. Why is it not a rational expression? Well, you can kind of get the idea with the word rational. If you think of rational numbers, we remember that, hey, things that use square root, like square root 2, are not rational numbers unless it plays out evenly. Well, this is the reason why it's not a rational expression. Some people might call it a transcendental expression or an irrational expression. I am just going to say it is not a rational expression. So, that is what an irrational expression is. This is your definition. Then we got to move on to what is a domain. The entire time when we've been doing math, we have been kind of avoiding the word domain. Domain. Domain is all possible x value. It's all possible x value for your expression. The way I like to think about it, it's where your function lives for x values, or where your expression So the reason why we have kind of ignored it is because thankfully many of the stuff we have been working with, our domain has been the entire real world or real number system. So let's give an example. Domain of, let's take x squared plus 2x plus 3. The domain of this is all possible x values, all real numbers, and that's it. It's just all real numbers. And why is this the case? Well, I can plug in any real number for x. If I plug in 1 for x, suppose x equals 1. Suppose x equals 1. Then I have 1 squared plus 2 times 1 plus 3, which is going to be 1 plus 2 plus 3, which is 1 plus 2 is 3, so we get 6. Notice that no matter what value I plug in for x, I will always spit out a real number. I can plug in a real number and I'll spit back out a real number. That is the idea of domain. The problem is, what happens if I plug in a number and I don't get a real number? Instead, I get an error, or I get a complex number. It's the idea of, hey, if you put this in your calculator, it'll mess up your calculator. So, generally speaking, the functions and expressions we have been working with are going to be all real numbers. However, there are a few exceptions that we got to talk about. Exceptions? Square root x and 1 over x. These are the two main ones that kind of mess up the domain of your expression. Now, when you get into calculus or whatever, you learn there are dozens of functions that have poor domains. However, for our class, for real numbers at the moment, these are the main reason why. And why is this true? Let's look at square root. What is the square root function? If I think of the square root function, if I take away, if I observe, let's look at square root of 9. Well, I can calculate that. That is 3. Great. Well, square root of, let's say, 2. I don't know the exact number, but I can calculate that as 1.4, yada yada, all the stuff. The triple dots represents the number goes on. I don't know what the other numbers are, but they go on. So I can calculate that. So no matter what number so far, everything has worked out nicely. If I did square root of 0, I get 0. However, what is square root of a negative real number? Negative 1. So this is the statement of saying, hey, what value, what value, I don't know what it is, but what value raised to the second power gives me negative 1? What number times itself will give me negative 1? Hopefully you see that issue. The issue is you might think it's negative 1, but the problem is a negative times a negative will always give me a positive. So if a number multiplied by itself gives me a positive, how can I reach a negative value? That's the reason why this expression is the domain of this guy. Domain of this guy is going to be all the x, all the real numbers, not integers, all the real numbers, such that x is bigger than or equal to 0. You have to be bigger than 0, bigger than or equal to. You can't have 0, you can, but you have to also be, a positive answer as well. Square root of 0, 0, everything past that, we're good to go. So that's the reason why square root x domain, we're not going to capture any negative values. We cannot for real numbers. If I plug in a negative value, I will not get a real number. If you try it on your calculator, you might get an error. Later on, we'll talk about what it actually is. Now, domain for 1 over x. Well, you've heard the statement before. You can't divide by 0. You can plug any number for x, even a negative number. 1 divided by negative 2, that's just negative 1/2. However, you cannot divide by 0. So the domain of this guy, as long as your denominator cannot be 0, denominator can't be 0. Can't be 0. So the domain of this guy is going to be all x that are real numbers such that x does not equal 0. I'll write this real quick. Such that x does not equal 0. And remember, these little notations that I'm showing you, this is set builder notation. Set builder. If you want to write it in interval notation, this is the same thing as saying, hey, you start from 0 and you're including it all the way to infinity. If you remember that. For your domain over here, the set builder notation, I've never introduced the infinity symbol. However, that's how you would write it in set builder notation. I mean interval notation, I apologize. You could also write this as negative infinity all the way to 0, union 0 to infinity. That's another way of writing. You can even graph it. So that's the domain, or that's examples of unique domains outside of just being all reals like we've worked with over here. So now we got to move into more complicated domains. So complicated domains. So now we want to see, hey, what is the domain of, let's take x over x squared minus 5x plus 6. That might seem like a hard one. Well, what you should recognize already is that this bottom part relates to 1.3. We can factor that guy. Factor. If we factor that, this is written as x minus 3, x minus 2. That's what we should get. Now, if we recall earlier, we have to, our domain for rational expressions, it's going to be all real numbers right here. All real numbers except if the denominator is 0. That is the only case. Well, notice that this is multiplying each other. They're multiplying. If they're multiplying each other, do we agree that any number times 0 is 0? That is the only case where our denominator can be 0. If one of these is 0, then we can't use. If one of these is 0, then we cannot use. Well, what would cause x minus 3 to be equal to 0? Well, let's just do that real quick. X minus 3 equals 0. And then we also have x minus 2 equals 0. If we add 3 to both sides, we get x is equal to 3. Add 2 to both sides, we get x equals 2. Now, what does this mean? This is what's going to happen. This is the numbers for x that are going to cause our fraction to have a denominator of 0. So this may look confusing, but our domain is actually going to be all real numbers such that x does not equal 3 and x does not equal 2. You cannot have them equal to this value. And why? If I plug in those values, your denominator will be 0. So you got to be very careful with that. Many times when people do mathematics and everything, they see this argument of contradictions. And most likely, the argument of contradiction happens because they're messing with their domain. So don't fall for that trap. People divide by 0 by accident or whatnot. So that's an example of one domain or one complicated domain. Let's go take another one. Let's take square root of x over, let's do x minus 5. Square root of x over x minus 5. Well, I know in this piece right here, I cannot have x equals 5 because 5 minus 5 gives me 0. And in this piece right here, I can only have positive value. So x has to be bigger than or equal to 0. So if I combine those two together, my statement says, hey, it's going to be all x in the real numbers such that x is strictly bigger than 0, or not strictly, I'm sorry, is greater than or equal to 0, and x does not equal 5. So it's okay to write some words into your subnote notation. Namely, the words you can use are such like and or, those kind of connectors, or conjunction. All right, moving forward. Where are we at currently? Now, we need to talk about, hey, if I have a rational expression, so this covers domain. If I have a rational expression, how do I know how to simplify? Simplifying. Well, simplifying is actually pretty easy. If I have AC over AB or BC, this is going to simplify to A over B. Which means if I have factors or things that are multiplying each other, then I can simplify it. So example, 5 times 2 over 3 times 2. I can cancel out that 5 or that those 2's. When you cancel out, remember, they turn into 1, not 0. So be careful on that. 5 divided by 3. Another example. That's one example. Another example. Well, let's say I have x plus 3 times x plus 2 over x times x plus 2. This is all multiplication. Remember that. Even though I see multiple terms, we can treat these two as giant objects, giant factors of multiplication. Notice I didn't do anything about addition. This is all, simplifying is only for multiplication. However, these additions that you see, they're inside your groups. The groups itself are all multiplying. So then if I do this, I can actually cancel out the x plus 2 and x plus 2. So I'm remaining with x plus 3 over x. You can use parentheses if you want to, just to signify it's just one object. That's up to you, though. Now, warning. Warning. I'm going to see this a lot on tests and stuff. And I'm going to count points off. Warning. Cannot do you cannot cancel these guys out. Why? Because these are different terms. Nothing is multiplying in this case. You cannot multiply a term with another term. That's not how it works. You cancel out factors. Cancel out factors, not terms. You cannot cancel out terms. You cancel out factors. There's a big difference. Factors are all multiplication. Terms are separated by addition and subtraction, so you cannot cancel it out. So you have to be careful. Even if I had an x here and a y here and an x here and a y here, I cannot cancel those x and y's. I cannot. You have to turn your problem into complete multiplication in order to do any sort of canceling out. This is super, super important. I don't know what symbol you guys use for your notes, but be sure you do not make this mistake. It is very common. So now let's talk about multiplying. All right, we know how to multiply fractions. We should have not lost our memory on that. If I have AB over BC, that's going to be the same thing. Oops. Let me use some different letters. If I have A over B times C over D, that is just multiplying straight across. There is one small thing I want to note with rational expression, though. So note, factor first, then cancel at the end. That's my little warning or note. Factor first, then cancel at the end for rational multiplication. Rational expression multiplication. We can do fractions, but now if we do rational expressions, let's take, where's my example at? Let's take x squared plus 2x minus 3 all over x squared plus 8x plus 16 times 3x plus 12 over x minus 1. This already looks messy. However, if we call back, this is why I wanted to hammer down factoring. If we factor the first one, the numerator of the first term, or first factor, we get x minus, or x, what is that? Minus 1 times x plus 3 all over x plus, what is that? 4 times x plus 4 times, if I factor it out, I get 3. If I do factor by GCF, I get x plus 4, x minus 1. Boom. Now, we're going to put them together. All of them are going to join together. Because if I for multiplication, you just multiply straight across. So if I multiply them straight across, I get x minus 1 times x minus 3 times 3 times x minus x plus 4, x plus 4. I'm just going to write x plus 4 squared. It means the exact same thing as x plus 4 times x plus 4, x minus 1. Well, in this case, we've already factored it out. Great. Now we need to do some cancellation. Well, what are the exact same factors? Notice that all of these are multiplication. All of these big objects. So now I can cancel things out. I cannot cancel this -1 and -1. That is not how it works. You have to cancel the entire object. So I'm canceling out x minus 1, x minus 1. Boom. And now I can cancel x plus 4 here. This is raised to the first power now. So now that I cancel out everything, this problem now turns into x minus 3 times 3. I move the 3 to the left side because I can do that. Remember, multiplication is commutative. I can rearrange how I multiply. All over x plus 4. Boom. And if you want to do the domain is all real numbers except x equals -4. That's one example. Let's do another example of multiplying. Do I have another example? Let's see. Well, I'll make up an example. X plus 3. Let's do x. Let's do 1 here. And then I in particular want to do x plus 5. X squared plus, let's do 8x plus 15. If I multiply this out, multiply straight across, I get x. Oh, first we got to factor, actually. I apologize. So if we factor this out, we get x plus 3 over x plus 5 times 1 over x plus 3 times x plus 5. And then now that I've multiplied it out, or now that I've actually factored it out, I can multiply them across. So I get x plus 3. 1 times anything is itself. All over x plus 5, x plus 5, x plus 3. And then if I cancel things out, the top counts as one giant object. I can cancel x plus 3 and x plus 3. And then I have nothing remaining at 1. Well, remember, if you cancel everything out, you're not left with 0. Rather, you're left with 1 over x plus 5 squared. So be sure you be careful on that when you cancel things out. There's going to be a 1 remaining. All right. Now, division. Division is just as easy as multiplication. Division. Division. And we're only going to do 1 because it's not too bad at all. X minus 4 over x squared minus 4 divided by x squared minus 3x minus 4 all over x squared plus 5x plus 6. All right, if we remember from fractions, to do division, all we have to do is keep change flip or turn the division to multiplication and reciprocate your second term. So for the first term, or before we even start that off, let's just factor everything out. If I factor everything out, I get x minus 4, and then the factor of this is almost a perfect square. However, we do know how to deal with it. Remember, if there's no middle term, we can add a 0 times x. So if we do that, we get x minus 4 times x plus 4 divided by x minus 4 x plus 1 all over x plus 3 x plus 2. This is what you should get when you factor it out. Eventually, you guys will get very comfortable with factoring. Now that I have that, I turn division into multiplication. Rewrite the problem now in different color, actually. I would like it if it was a different color. X minus 4 over x minus 4 x plus 4. And I'm just going to put a parentheses on everything so I can see it's a giant object. And I'm turning division into multiplication. But if I do that, I have to multiply its inverse or reciprocal. So it's going to be x plus 3, x plus 2, x minus 4, x plus 1. Now, I can actually multiply them out. If I multiply them, I have x minus 4. Now, some people can cancel out right here. You can do that. I'm just multiplying them out to just show my work. So I'm adding an additional step. All over x minus 4, x plus 4, x minus 4, x plus 1. See, the problem with division and multiplication rational expressions, it is not a bad problem at all. Actually, it's very easy to do. Now, some expressions are very big, so you have to write a lot. However, it is not a difficult problem. So now when I do my cancellation, x minus 4 cancels with x minus 4. What else do we have? I think that's it. I think those are the only terms that cancel out, unless I'm missing a term. X plus 3, x plus 2, x plus 4, x minus 4. And they can only cancel out if one's on top and one's on bottom. So what am I remaining with? I'm remaining with x plus 3, x plus 2, all over x plus 4, x minus 4, x plus 1. And now, I am not going to be too picky on you actually multiplying these all out. No, you can just leave it in factored form. However, when you're doing addition or subtraction, that's where things change. That is a much harder thing to deal with than multiplication or division. So, speaking of that, we actually have to get with addition. Let's see, I'll scroll down. Adding rational expression. It's kind of like fractions. Multiplying fractions is easy. Dividing fraction is easy. But when you add, some things can become ridiculous. So you need, like fractions, need same denominator. You need the same denominator. You have to have the same denominator. So let's do an example. Three over x plus minus 1 plus x over x plus 2. Boom. All right, if we're adding these are not the same denominator, so I can't just add the top piece. And I don't recommend, I guess I'll say this, only, well, I'm not even going to say that yet. But I don't recommend trying to guess a random factor here. That can be ridiculous. These guys, the lowest common denominator, if you recall back, if you have trouble finding that, just multiply them out. Multiply them out. So what I'm going to do is, and multiplying them out does not mean you have to actually express it out. What I mean by that is, hey, if I want the same denominator, I can multiply the first term by x plus 2 over x plus 2. And I can multiply the second guy by x minus 1, x minus 1. So then this is 3 over x minus 1. Oops. 3 over x minus 1. And this is going to be plus x over x plus 2. These guys are multiplying each other. Boom. If I multiply them out, I'm going to get 3x plus 2 plus x plus 2, x minus 1, and then x times x minus 1 over x plus 2, x minus 1. Boom. Now, my tip for you guys is when you guys are adding or subtracting, you almost never want to multiply the denominator out. You almost never want to expand your denominator. However, your numerator, you need to expand. And why do I need to expand the numerator? Because this addition is messing things up. The denominator, well, if I actually add these together, we're going to have 3x plus 2 plus x times x minus 1 all over the same denominator, right? That's how fractions work. They have the same denominator. Well, the denominator doesn't have any addition. They're both just broken down to factors. They're multiplying only. However, the top, I see two giant objects, two giant terms. One term, two terms. And if I see more than one term, that automatically means we are not in factored form. So I have to add this first. Or I have to expand it. Expand. So let's expand it out. If I distribute this 3 over, and if I distribute this x over, I get, in purple, 3x plus 6 plus x squared minus x all over x plus 2 and x minus 1. And why do we do this? Well, sometimes when you expand it, you can combine like terms. And when you combine like terms, you might have a new problem. So let's combine like terms. If I combine like term, I get x squared. My like terms are only right here. Plus 2x plus 6. Is it 2x plus 6? I believe it is. Let me just see and verify if I have the right problem or not. Where am I at? Yep, we're good to go. All over x plus 2 times x minus 1. Anything cancel out? I think that's it. And then, fortunately, this piece not factorable. Why? Because the factors of 6 are only 1 and 6, and the other one is 2 and 3. No option possible will give me 2 if I add them together. So, this is not factorable. However, if it was factorable because you combine like terms, you would have to do some cancellation. So that's the reason why I say when you do an addition or subtraction, you might actually have to expand the numerator. You will generally need to expand the numerator. Your denominator, I did not recommend multiplying them out. But your numerator, yes you do. So we'll do another example, this time with subtraction. Subtraction always gets students. So I have, let's do 1 over, let me use a different color now. 1 over x squared minus 1. Subtract it to 2 over x plus 1 squared. And I've told you, I hate dealing with subtraction, so if you recall that, I told you how to deal with subtraction. Instead of subtracting, we're going to turn this guy into addition. And while we're doing that, I'm already going to factor as much as possible to problems. So this is going to turn into 1 over x plus 1, x minus 1. And then this is going to turn to addition. But if I turn that into addition, I have to apply the negative to my fraction. Now, a little heads up. If you have a fraction, let's say 1/2, if I apply a negative to it, if I want to do a negative, the negative can go on top, it can go on bottom, it could go on the entire fraction, but it cannot be on both. Why? Because a negative divided by a negative is a positive. So if you have a negative, choose where to put it. I'm going to put it on the numerator. Now if I put it on the numerator, it has to go to everything on the numerator. Be careful of that. Right now we only have 2 as our numerator. However, if this was, let's say, 2 plus x, I will have to apply the negative to that x. So be very careful on that. All right. So now that I have this, I need the exact same denominator. So I need to find the least common denominator. However, this is x plus 1, x minus 1. This guy right here is just x plus 1 times x plus 1. Well, if we think of it like this, the least common denominator, what can I multiply? Oops, let's see. What can I multiply? Let's see. Where's it at? What can I multiply both of them so they can have the exact same denominator? I should write this neater. Let me write this neater. Let's write it over here actually. 1 over x plus 1, x minus 1, plus negative 2 over x plus 1 times x plus 1. Well, we see that the green one is missing an x minus 1. So I do need to multiply this by x minus 1. However, the first term still is missing a piece. I have to get the same exact denominator, we're going to have in total 3 different factors. 1, 2, 3. So the first term, you need to multiply that by x plus 1 over x plus 1. And that's because it's missing an x plus 1 from this guy. It's missing that. So I need to give it an x plus 1. After we multiplied it, or now that we multiplied them out, let's actually write it down. So multiplying them out, I get x plus 1 all over x plus 1. I am not going to multiply the denominator out. It's just going to leave it that way. Plus negative 2x minus 1 all over the same exact denominator. Now I'm going to distribute this 2 out. Boom. And I'm actually going to turn this into one fraction. The denominator is the exact same. So now, with the same exact denominator, I have x plus 1, x plus 1, x minus 1. Your numerator is going to be x plus 1 plus, well, negative 2 times x. That's going to be negative 2x. And then negative 2 times negative 1. A negative times a negative is a positive. Remember, the negative goes to that 1. We get plus 2. And then I have to combine like terms. Well, my like terms are going to be negative 2x. And it's going to be plus 1 and plus 2. And in doing so, I actually have, what is that? Negative x plus 3 all over x plus 1, x plus 1, x minus 1. Boom. So in this case, nothing still cancels out, thankfully. So that's how you do subtraction. This is how you do addition. But yeah, just be aware, you might have to cancel things out at the very end after you combine like terms. So moving on, we got one more thing to talk about, two more things to talk about, and then we're done. So now we talk about compound rational expressions. We talked about compound fractions before, and compound fraction is just a fraction divided by a fraction. So if I gave you x over y plus 1 over 1 minus y over x. Now that we've done with just numbers, we can actually do rational expressions. Well, let's look at them by components. Let's look at the numerator and let's look at the denominator. How can I add x over y plus 1? Well, this is the same thing I say, x over y plus y over y. That'll give me the same denominator. And for your denominator of the entire fraction, this is going to be x over x minus y over x. Because your denominator is x, and then there's 1, just multiply by x. I mean, it's just going to be x over x. And now we can actually add the top with the top and the bottom with, or not at the top with top. We can combine the numerator and we can combine the denominators out. My wording is pretty bad when I'm talking about multiple fractions together. So I apologize for that. I want to do purple. There we go. So if I add them two together, they have the same denominator now. So I can do x plus y all over y divided by x minus y over x. And remember, if this is uncomfortable, this notation is uncomfortable to you, you can turn that into division if you want to. Or the other division symbol. You can just write it as the other division symbol if it makes you feel uncomfortable. Boom. Now we're doing division. Well, to do division, we turn that into multiplication. But if I turn it into multiplication, I have to flip or reciprocate the second term. So it's going to be x over x minus y. Now let's actually calculate this out. Well, I have x over x plus y all over y times x minus y. Boom. Now, be very careful because in this case, nothing cancels out. You might think you cancel out this term and this term. However, this plus sign and minus sign automatically tells you, hey, these two objects are not the same. They are not the same because one of them has add, one of them has addition. You cannot cancel them out. So this is as simplified as you can get for this compound rational expression. And then the last thing we'll talk about is rationalizing. Rationalizing. So sometimes you have to rationalize problems. Like let's suppose I have 1 over 1 plus square root 2. We know how to deal with it if it was one single term in your denominator. You would multiply it by square root 2 over square root 2. However, if I do that for this problem, I will still have a radical in my denominator. I am not going to be heavily expecting you to rationalize the numerator, but I always generally expect you to rationalize the denominator. Now, in calculus, they might require in some problems to rationalize the numerator, and you do the same procedures. So, this is a term called conjugate. So, we got to do conjugate. The word con means with. The word jugate means pair. So, it's the same, it's with a pair. So, a conjugate, we're going to define that as a term in the form of A plus B has the conjugate. I'm going to do radical right there. Has the conjugate A minus root B. So it's kind of like the opposite in that aspect, like the mirrored world or whatever you want to think about. It's the one that comes with that pair or the opposite of the pair. It's kind of like that twin or something. I don't know. So conjugate. For this problem in rationalizing, the idea is that you're going to multiply conjugate of denominator. So I have to get the conjugate of 1 plus square root 2, which by following our definition, this is 1 plus square root 2. I'm going to multiply this by 1 minus square root 2. However, if I multiply it by that, I change the problem. So if you remember, we divide that by 1 minus square root 2 as well, because we want to multiply by 1 so we do not change the value at all. And if I do that, I get, well, 1 times anything is itself, so we're going to have 1 minus square root 2 all over, let me do a different color now, purple, all over, well, this is multiplying this. You have to FOIL this out. Boom, 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 boom. Be sure you FOIL that out. If you FOIL it out, you get 1, what is that? This is minus 2, and then plus 2 root 2. I want to say that. Let's see. Nope, the middle term gets deleted. I apologize. So well, you get 1 minus 2. So your radical is removed in that case. Your square root 2's will get removed. And if you do that, well, let me be more specific. This is actually square root 4. If you didn't see that. And then this becomes 1 minus square root 2 all over 1 minus 2, which is going to give you 1 minus root 2 over negative 1. So your final answer should be, I have to write it over here, so I apologize. Or the simplified version is going to be negative of 1 minus square root 2, which you can simplify that as negative 1 plus square root 2. The reason why that's the case is because, hey, if I divide something by negative 1, that's the same as turning it negative. That's the same as multiplying by negative 1. And that is conjugate. So give that a shot and all that good stuff. And that's pretty much what covers rational expressions. So the key thing is, when you're going above here, is, hey, if I do multiplication, where's that multiplication, and division, it should be relatively easy. The only hard part about multiplication and division is writing the terms out and maybe factoring. But the problem becomes when you do addition. When you're doing addition, well, not only do you have to find the least common denominator, that means you have to be comfortable with finding factors. I'd recommend expressing your denominator as factors. So factor your denominator as much as possible, and then you can see what you need to multiply by to get the same denominator. Then, after you do that, you might have to actually combine like terms for the numerator. You might actually have to expand it. You might have to distribute. And then if you do that, you might actually have to cancel some things out with the denominator. Do not expand the denominator. Do not multiply the denominator out. It's best just to leave it the way it is. Compound fractions, yep, that should be good to go. Rationalizing, and that concludes 1.4. And now we have enough materials for the homework assignments. So I will catch you guys later. Take care.